In this lecture, we are going to learn about single source shortest path with negative length of edges. Okay, so we have already seen some algorithms for single source shortest path. So there is a graph, you have a single source, there are a lot of other nodes, and you want to find the shortest path from this node. But the thing is here some speciality, that is there is that your edges can have negative weights. Okay, so how will you handle that case? So Dijkstra's algorithm fails for your negative weight edges. So how to handle this? So we will now look at Bellman-Ford algorithm. Okay, so this algorithm works even for your negative weight edges. So let's try to see. Here is an example. Suppose we allow edges to have negative length. Okay, so for this example, let's see. So here we have negative length. So A to C is 3, A to B is 4 in this graph, and B to C. So now is it true? So what will be the, in just looking at this graph and getting a feel about negative weight edges, so what will be the minimum shortest distance from A to C? I can directly reach here, cost is 3. But if you go via B, then A to B, B to C, it's 4 plus minus 2. So it's just 2. So 2 is the shortest path from A to C. For B, now what will be the shortest path? From A to B it's 4, but so this is the source. So A to B via C, so it's just 1. So this will be the shortest path. Okay, but so let's try to see. A to this might not be, okay, might not, it should not be, because this is a directed graph. Okay, so directed graph, I cannot reach this one. So C will be 4 minus 2, 2, but B it will be 4 only, because I cannot travel from C to B, because it's a directed graph. Okay, so now let's try to see further. So this is there. So Dijkstra's algorithm can fail. Okay, so why will Dijkstra's algorithm fail for negative weight cycles? Okay, so what will be the problem with the Dijkstra's algorithm? So let's try to analyze that. So Dijkstra's algorithm is more efficient in terms of Bellman-Ford if the edges are positive. Okay, but let's try to see why it fails. So let's say we have a path, shortest path from S to V1 to V2 and then finally to Vk. So Dijkstra's algorithm assumes that when you have ds to Vi should be less than equal to ds comma Vk, where your I is less than k. So why will this be true? Because for example S, V1, V2, V3, so now shortest path, so let's say it is 2, this is 3, this is minus 4. So now what will happen, if this is the shortest path, then this assumption will become false, because what will happen, ds to V2 will be 5, but ds to V3, because of this negative weight edge, will be 2 plus 3, 5 minus 4, 1. Okay, so this is in fact nearer than V1. So that's why Dijkstra's algorithm will fail here, because it considers that this is the order. So your path length will always increase if you are going farther in the shortest path route. So now let's try to see about some negative length cycles. So in fact cycles, what they will do, they are kind of a special case. So if you have a cycle, negative length cycle, and with total weight less than 0, then this will destroy, in fact in that case your shortest path will be minus infinity. So let's try to look here. So in this cycle is a negative cycle if sum of the edges length is less than 0. And let's see this graph. So if S can reach a negative cycle C and C can reach T, Okay, so S can reach some negative cycle, okay, C, and from C you can reach T, then the shortest path length will be minus infinity. So this is in fact simple. So I have S to T I want to go in this graph, and S to this cycle C, this part I go, and now this is 4 plus 3 7 and minus 8. So this is a negative cycle. Okay, so when I go 1 2, this is 3 now coming to this node, but then after that I will keep cycling here in this cycle, roaming around, and then what will happen? Every time I will gain minus 1. So if I do like this, I can do infinite number of times, and then some time I will reach T. So this T is also has distance minus infinity. So moving forward, so if in any graph, if source is there and some negative cycle is reachable, so and then you can reach some node T, so they will have negative infinite, minus infinity will be the shortest path. So this is there. So now let's try to see single short source shortest path with negative length. So given G with edges length and they can be negative, and given a source and T is the destination, okay, so you have to find the shortest path and show that it is minus infinity by, and if it has a negative cycle you can show that it is minus infinity. Okay, so we will assume here that we don't have any negative cycles for now, because if there is a negative cycles, your whatever nodes are connected, they will have in minus infinity as the distance. So what happens is in Bellman-Ford algorithm, first thing is that there are two important things, and one in fact is the most important, is the update method. Okay, so there exists a shortest path. Okay, so S to V1 to V2 to V3 then Vk, then we will keep what a distance U, which is an overestimate of the shortest path distance. Okay, and finally when the algorithm terminates, it becomes equal to the shortest path from S to U. So initially we make all those infinite. Okay, all the distance except for S, we make it infinite, and then we do a very interesting update or relax function, which we will look now. So we have update. So update I think is a better function name than relaxation. Okay, so we have update edge U comma V. So what it means is, let's say we have a distance like this. Initially there was a source, there is some graph like this, and now let's say we are here. So initially it was 20. Now what is there? So D of V is 20, D of U is 10. So what will happen? So if distance of V presently from the source is greater than distance of U plus this edge weight, okay, then what will we do? We will update, because I know now that there is a shorter path from U to V, and we will update it here. So 20 is greater than D of U is 10 plus 5 is the edge weight. Then we will update D of V to be 15. Okay, so that's there. Otherwise we will leave it. It's better now. Okay, so this is there. Next we look. So now what happens? There exists the shortest path is there, so E always is update, and this update is even safe when you have negative length edges. So why is that true? So even if you have negative weight edges, then also this update method will work. So why? That's the question. So what will happen? So you have du here, so there is a source S, and du and v is there, d of v. So what will happen? If there is a negative edge, then also we can just update, it will decrease the value of dv, then it is fine, we can take it. So that's there. Now what happens? Order of updates. So if updates from S to V1, then V1 to V2, so the path is V1, V2 till Vk. To T is the shortest path. So this is the destination. So if we update, make the updates, okay, so in this order, first we make the update S to V1, then V1 to V2, then V2 to V3, then Vk minus 1 to Vk, and finally Vk to T. Then what will happen? This distance of Vk is the correct shortest path. Okay, that's there. If you do the update in this order, so it will be perfect and you will get the shortest path. But the problem is that we don't know this shortest path. Okay, because if you know the shortest path, then there is no need to update, just as those edges. So what we do? So we observe that if we have mod v equal to n, let's say n vertices or nodes are there, then we know that for a simple path the maximum number of edges between source and your destination will be n minus 1. Okay, you cannot have more distance than this in a simple path. So what we do, and then what happens is, so this is the maximum hop length that can be there between S and T. So we don't know the order, so what we do, we run this update method for all the edges n minus 1 times. Okay, so we will see this thing. So we don't know which is the shortest path, so we update all the edges and iterate mod v minus 1 times. Okay, so let's try to see now the algorithm. So we are given a graph with vertices and edges and edge lengths L of E, and they can be negative also. So what we do initially we make, for all the nodes in that graph, we have distance of u is equal to infinity except the source which is connected to itself, and distance of S is 0. Then what we do, for I is equal to 1 to mod v minus 1. Okay, so all the number of nodes. Okay, so what we do, for all edges uv we update the edge. So this is a simple algorithm, and then we return the distance value. So this is the algorithm. Okay, so now we will try to see this for one particular algorithm. Okay, so here we have a graph. Okay, so this graph S, T, A and B are there, and we will update. Okay, so you have to basically follow how you take the edges. Let's say I take the edges in the order, so S A, then A T, and then you take T comma B, and then A comma B and S comma B. Okay, so I will take it in, there are 5 edges, I will take in this order. Okay, so what was the algorithm? So we just try to see. So for each edge, so we iterate mod v minus 1 times, and for each edge uv update E. So that's there, that's simple algorithm, and we move down. Okay, so now let's try to see. So this is our edges. Okay, so it has gone, so SA, then okay, now we have this order. Okay, AB, then SB, AT and TB. Okay, so this is the order. So now initially I run, so how many nodes are there? So 4 nodes, so I will run 3 times. Mod v minus 1 is equal to 3. So there are 1 2 3 4 nodes are there, so 3 times I will run, and in this order I will relax. So let's see what will happen. So initially everything is infinity, this one is 0, so I will make my S A B T here. Okay, and then iteration 1 2 and 3. Okay, and let's say what are the values that come, and this is iteration 0. Okay, so initialization, in this is 0, this is infinity, this is infinity, this is infinity. Now what happens, we will fill the values. So what happens, initially I start from S to A, I update. So what is the A now? It's infinity, D of A is infinity. So now I make it equal to 5 because d of s 0 plus 5 is, so a will become, now, so phone is ringing, so I cannot do anything, so it becomes 5 now. And now I go to a to b. So a to b, in this one now d of a is 5. Okay, so d of a is 5 and b is now infinity, so 5 minus 2, it becomes 3, and it's good, so it becomes 3 here. And then we do s to b, so b was 3 now, and from here 0 plus 4, it is becoming 4, so I will not update in fact. And then I go to a to t, so a is 5, a is 5, t is now infinity, so 5 plus 6, 11 it will become. This is my first iteration. Okay, so after the first iteration, you see what happens is at least all the distance 1 nodes will have correct values. So I have 0, 5 here, and then you have I have 3 here and 11. Okay, and now what happens in iteration 2, I will go. So what we will see, so let's try to see. So now what will happen is, we see here that in the next iteration again we will start SA. So now also S is 0, A will be 5, so this is same, so this will be 0, this will be 5. B, so in B what happens, again A to B I go, so A is 5 and B is minus 2, so 3. This is the same here, so it will remain the same. S to B, so S to B if you go, it is 4 and it was already 3, so there's no update needed. T, so it was 11. Okay, so what will happen, S to B is done. A to T, so again 5 plus 6, 11. T to B now, so T to B now it will work, so it is 11 minus 9, so it is becoming a 2, so it will get updated, so it will become a 2 here. Okay, and this was 11. Now in the third iteration again we will iterate, and what will happen, S to A 5, it will remain 5. A to B, so now update, so 5 minus 2, 3, so in fact it is greater than what is already there, so it will remain a 2. S to B will also not work. A to T, so 5 plus 6, 11 it will remain, and T to B it was, so it will update and it is already 2, so it will remain like this, so this will be 11. Okay, so now we see finally that 0, 5 to 11 are the final shortest distance from S to T. So this is what is needed. So after this, even there was some negative weights, so now you see that from S we go from 5 plus 6, 11 minus 9, so this 3 hop length is the shortest path. So this is there for the Bellman-Ford algorithm, how you run it. Okay, and they have in fact taken here some different, so for all edges when you do, so in this one they have taken some different order, so whatever order you take finally, because you are iterating v minus 1 times, so it will work fine, because they are relaxing in different orders, but because you are relaxing the maximum number of times, that is mod of v minus 1 times, so it will work. So this is there. Now let's try to see why it is correct. So consider the shortest path S to T, which is going via v1, v2, vk. Okay, and then what we observe, if I is less than k, then S to v1, v2 till vi is shortest path in S to vi. So that will be true, isn't it? Because otherwise if there is some other shortest path, we will take that. So S to vi. Now what happens? After iteration 1, what will happen is distance of v1 from S, okay, will, because of the update s to v1, this will become the shortest. So in iteration 1, one hop distance, the first node v1 will have the shortest path because of the update from v1. After iteration 2, now distance of v2 will be equal to distance of s comma v2, because what happens, distance of v1 was correct in the first iteration. Okay, so because one hop distances, so v1 was correct in the previous iteration, so now v1 to v2 relaxation will be done, and because of that v2 will also have a correct distance. And so by induction, if you run n minus 1 times, where n is the number of nodes, all nodes are, you are sure to get the correct path. So this is there for the Bellman-Ford algorithm. I hope you understand this. Thanks a lot.